This week's lab is the separation of cyclohexane and toluene by distillation. As a summary, you will be distilling a 50-50 cyclohexane toluene mixture using simple and fractional distillation. Due to COVID restrictions and social distancing, as well as time, you will be assigned either the simple or a fractional distillation. Please keep in mind you need to be familiar with both of these techniques for your technique check that will happen at midterm and at the final. Once you have completed your distillation, you'll take the refractive index of the separated fractions to compare the purity of each component that you have distilled. I'll discuss refractive index at the end of this pre-lab lecture. Just as a bit of a reminder, you're probably familiar with distillation to some degree from your discussion of gas laws in general chemistry. Distillation is considered a separation technique. It allows us to separate compounds based on their boiling points. If you have two compounds, one of them is going to be more volatile than the other or have a lower boiling point. That compound is going to be the compound that is first converted into the vapor phase due to the heat and energy transfer, which means that that would be the compound that would distill off first. The vapors of that compound will need to be converted back into liquid. They do that going through a condenser column, and ultimately the liquid will be collected and analyzed for purity. A little bit of a reminder about boiling down here on the slide. It is dictated by equilibrium vapor pressure, and in ideal two-compound solutions, the vapor composition is dictated by Raoult's law, as you can see here. I'm not going to actually ask you guys to memorize these formulas or to even calculate vapor pressure or vapor composition based on any of the equations in the lab book. So if you remember what miscible liquids are, they're two liquids that are completely soluble in one another. Miscible liquids will boil at a temperature between the boiling points of the two compounds, the two pure compounds. The exact mixture boiling point is dictated by what the composition is, whether it's 50-50 like in our case, or if it's 40-60. We see this kind of comparison of exact mixture boiling point versus proportions over in figure 1, where we see a variety of percent toluenes versus percent cyclohexanes and the mixture boiling points. The vapor of miscible liquids will be different from the composition of the liquid mixture it came from. That's because the vapor should always contain more of the low boiling compound. The composition change, that composition change from the liquid mixture versus the vapor mixture, allows for us to actually do this separation. Ultimately, it's what allows us to successfully distill and purify two compounds from one another. And we see over here on the right, figure 2, that's showing kind of the vapor curve and the vaporizing of cyclohexane and toluene, indicating how your vapor is actually enriched in the lower boiling, in our case, cyclohexane component. You're doing two different techniques, two different distillations. One is simple distillation. All of ours are in macro scale, so that's the illustrations that you see from your lab book. Simple distillation is appropriate to use if your compounds are have a very large difference in their boiling points. So if one compound is much more volatile than the other. You'll see the simple distillation set up here. Also, we have a video of building the distillation setup that Travis put together. But you've got your pot where your liquid solution resides. You have a short distilling head as well as a thermometer for reading out temperatures. Your condenser column that will have water running through, what we call a water jacket, to help cool your vapors down. And then, of course, you need a receiver. Our receivers will be graduated cylinders so we can analyze the volume that we're collecting. Fractional distillation must be used when your boiling points of the two compounds in the mixture are less than 40 degrees apart. Basically, what a fractional distillation does is many simple distillations thanks to the use of a fractionating column. And that's that new piece of glassware that you might notice in this illustration separating the pot or the round bottom from the distilling head where the thermometer is. You have this extra piece of glassware that's basically just a tall glass tube, and you will be able to watch condensation move up the height of that column. That's called the condensation line. What's happening is as the condensation line is moving, condensation of the vapors is occurring, and then due to the heat from the heat source, the liquid condensation is re-vaporized, and effectively many MINI distillations are occurring along the height of that column. This idea of condensation and revaporization is called the theoretical plate, and the more theoretical plates that occur for your fractional distillation, the more efficient your separation. So, of course, you could have many theoretical plates by putting in a taller column, by putting in something like we see in this illustration, like steel wool to provide lots of condensation locations. We'll be using an empty column for time purposes. The more theoretical plates that occur, the longer the distillation. But of course, the more pure compounds you tend to get out. Figure 5 is showing us kind of the effects of those theoretical plates, the small little simple distillations that keep occurring. And basically what we're seeing is that as each condensation and revaporization occurs, you're increasing the concentration of the more volatile compound. You need to make sure that you watch your rate. In our procedure video, I discuss what your rate should be. It should be about 1 drop per second, but if the distillation occurs too rapidly, regardless of whether you're using simple or fractional, but particularly fractional, your liquid vapor equilibrium can't be established in the column very quickly, and so you get poor separation in a technique that you should be getting excellent separation for. Please be observant and watch that condensation line, okay? You'll need to include lots of descriptions in your notes since this is a full lab report lab. But once the vapors from the condensation lab reach the thermometer bulb, you should see and observe a temperature increase. The observed temperature that you're reading from the thermometer should be close to the boiling point of the compound distilling off. So at first, it should be close to the lower boiling cyclohexane boiling point. Once that low boiling material, in our case cyclohexane, has distilled off, then you should see a sharp rise in temperature as vapors from the higher boiling point compound are finally reaching thermometer bulb. This happens very effectively and very noticeably in your fractional distillations. Simple distillations and poorly done fractional distillations tend to only see a gradual increase in temperature as opposed to this sharp increase. Figure 6 in your lab book is a nice illustration of this, and this is a graph that you will be making. You'll be sharing data, like I said, at your benches, but you will need to plot your fractional distillation curves versus your simple distillation curves. As I said earlier, you will be measuring your the 2 different fractions that you're collecting. So we'll collect the low boiling fraction and the high boiling fraction. And you will analyze it using refractive index, okay? Relative amounts of the compounds present in a sample can be determined by measuring this refractive index of a sample, and we see here in figure 7 a correlation curve that you can refer back to kind of help identify how pure your compound is based on your observed refractive index. To go over refractive index, since this lab has been moved to a makeup lab, refractive index is basically measured by comparing the angle of incidence of light in air to the angle of refraction of light through a liquid. So basically you're comparing how well light moves through air versus a liquid that you have put on an instrument, okay? And so that's what we see here in this equation 5, is this comparison. Again, I'm not gonna have you do anything about this equation, it's just getting you to understanding how you get this refractive index. Refractive index is typically measured at room temperature, and our refractive index refractometers, our refractive index measuring devices, are located in the room next door to the organic lab. Typically, you're measuring it at ambient temperature, and you apply a temperature correction for the reading. So here in this equation labeled equation 6 on the slide, we have N20D. The 20 stands for the temperature that value is recorded for, okay? And D is the sodium line. So we are observing our refractive indices at wavelengths of 589, the sodium line, which you may recall from Gen Chem is the D line, and the 20 is indicating the temperature. Now, we don't keep our rooms at 20 degrees Celsius, so the rest of that equation is showing how to adjust your refractive index measurement you're in for the temperature that the room is where you're measuring this. Our refractive index apparatus or refractometer looks very similar to the one in this illustration from Lab 2 in your lab books. It's an Abbey refractometer. Basically, you have prisms here, and you'll open this up. It's on a swing hinge, and you'll apply your liquid fractions to the prism here. You just need a thin layer for the light to go through. You have a light source here, so you'll need to make sure that the light is turned on and your refractometer is turned on. Because we're using prisms, we keep plastic pipettes by the refractometers. If you're not using it for very long, the plastic pipettes should be okay with the cyclohexane and toluene. You can use glass pipettes, but be careful, they will scratch your prisms. The eyepiece is up above, and you are looking through this eyepiece, and basically you're looking for a light and dark interface, and that's what the illustration in figure 11 on this slide is indicating. You want to line up the light-dark interface with a crosshairs that you should see through the eyepiece, and you also want that to be a sharp interface. You don't want it to be fuzzy, and ideally it may appear blue. Try adjusting the knob on the refractometer to make sure that you get the best light-dark interface possible and the sharpest line. Once you have it adjusted, you'll be able to push a button on our refractometers to read out what your refractive index measurement is, and then you will need to record the temperature from the room. One of our refractometers actually has a temperature measurement on it, so you can just record the temperature off of either your refractometer you're using or look at the other refractometer in the room. They're in the same room, so the temperature should be the same. The equation that I had on the last slide for temperature adjustment needs to be applied. Usually our room sits about 23 or 24 degrees C. Just to make you feel better, that equation is taped to the bench top. So you never have to memorize it. You can always refer back to it in your book. It's here both in the distillation lab as well as in lab 2, that adjusted temperature measurement. If you have any questions, be sure to contact me or one of your TAs.